Thanks for taking care of my mix-up.
That's okay.
I mean, we can start whenever you're comfortable, or and I can give the intro, and we can say, is this okay?
Yeah, this is okay.
Okay. Okay, so thank you then. Let me give a short intro. So hello, everybody. Welcome to the afternoon session. And we're very glad to have Dr. Lavanya Tekumulla with us. She's going to provide a very interesting perspective. I'll just give a brief background about Lavanya. She did her PhD from Indian Institute of Science and her master's from University of Utah. Since then, she's been involved in a number of machine learning entrepreneurship opportunities. She has been a machine learning scientist at Amazon and a founder in residence at Entrepreneur First, a consulting an ML scientist at Kinome, and currently she's the founder and machine learning specialist of AI Phonic Labs. And if you have seen the website, machinelearninginterview.com. So please correct me, Lavanya, if I'm wrong. So that's her baby too. Okay? Yeah. So over to you, Lavanya.
Thanks, Anirban. So I will share my screen. Just hold on. Can you see my screen?
Yes, we can see the screen.
Okay, so thank you for the introduction, Anirban. Let me just jump into today's talk. So today we want to talk about taking ML models to products. So you have seen in various other talks through this workshop, through the summer school, different ways to build models. So you have seen, like, there have been sessions on, like, supervised learning, unsupervised learning, Bayesian modeling. You might have had NLP, deep learning. So different types of models that you can build for various applications, right? But then how do you actually make sure that these models have impact, the kind of impact that you want on the business and on the customers? So you want to make sure they're useful for the customers in a company, right? If you're using them in industry. So how do you, what is the missing link there? So how do you make sure that your models are doing what they're supposed to do? So that's what we want to focus on in this talk. So there are going to be like, so I'm going to do part 1 and part 2. So probably going to leave out part 3. So part 1 is about understanding the process of machine learning product development. I'll do that with an example. And the second part is how to build fair and unbiased ML models. So again, we'll first go into the first part, and then I'll talk about that, because that's another important aspect of making sure that, you build machine learning pipelines that are useful for everybody and, do what you want them to do, achieve the outcome you want them to in our society. Okay, so for the first part, understanding the machine learning product development life cycle. So for this, I'm going to, talk about an example. This is just an example that I worked on way back, but it would be useful to sort of demonstrate all the aspects that are involved. Okay, so we're going to talk about the specific problem of product size recommendation in fashion e-commerce. So let's say that, you are shopping online in a website like Amazon or Flipkart or Myntra, right? And it's often, so if you want to shop stuff like apparel or shoes, right? It's often hard for people to choose fashion related stuff online because there's a problem with the size, right? So for example, different brands have different sizing conventions. Suppose I'm trying to buy shoes, right? So the Reebok size mapping could be like size 6 is 15 centimeters, size 7 is 17 centimeters. While the Nike mapping could be something like size 6 is 16 centimeters, size 7 is 18 centimeters. This is just an example. So the point is, the sizing conventions are not always easy to decipher. And it's also the case that sometimes, the product has like, maybe an old size chart because they haven't updated the size chart, or sometimes the size charts are just missing. right? So because of all these reasons, customers often choose an approximate size, and this results in a lot of returns. Okay, so we'll take this problem, and the problem here is, okay, what do I do? Can I actually build a machine learning model, or like, can I build something to actually solve this problem of making uh, customers choosing the right product size easier? So if you go to the website, you will see like, a product and there are many size variants. The idea is, how do you help the customer pick the right size, right? It's as simple as that. Now, so this is the example that we are going to look at. So now if you come to like, how a traditional machine learning product development lifecycle works. So before going into that, if you think of your regular program, typically you give some input and you give a program, which is some code that you write, right? And then the whatever function that you wrote will take the input, compute, and give you some result. But if you come to the machine learning product development lifecycle, typically you're going to like give an input and the desired result, which is like, your target variable. You're going to give it data basically, which might contain like, labeled instances. And then out comes the program or your model, which can compute the outcome on a new example, right? So what this means is that the kind of risks involved are different when you're trying to build, when you're working with an ML based project, right? So it's not as deterministic as that of a regular project typically. So in a regular project development lifecycle, I'm not going to go over this. It's just like, pretty straightforward. So you have some requirements analysis. You would have seen this somewhere or the other, this kind of a picture. Design, and then you design your code architecture, then you implement it, and then you test it, and then you evaluate it, and then keep iterating. If needed, you make more changes, right? But if you come to the machine learning product development lifecycle, it's much more complex, right? The reason being, you want to sort of mitigate the risks that are involved. So because when you say there are more risks involved, so in this case, right, if you give bad data, for instance, right, or you might not have sufficient data, or you might not be capturing data from one segment of population. So there are many reasons because of which the model that you get might work for a subset of your instances, but not for all the instances, right? Your model might not generalize well. So there are many question marks here. And because of that, the kind of impact that you want is harder to, it's harder for you to say whether you will achieve it or not when you're actually doing like a ML problem compared to, let's say, just writing a regular bit of code, right? And that's the reason you have like, many more steps typically when you're actually trying to work with a ML based project, right? So I'm going to briefly go over these things with our example of product size recommendation, right? So so the basic steps, the basic building blocks in an ML project lifecycle are as follows. The first is understanding the problem, the customer problem and the business problem. Then there is this block here. If you need ML, there's this block here where you actually gather the data and then you go over the data and understand, what all, try to get more insights from the data to figure out what kind of models you can use. And then there is a step of feasibility and impact analysis to understand whether the models that you have conceptualized are easy to implement and how you're going to implement them. Then you actually go ahead and implement those models, and then you need to test them, and then you need to roll them out. So let's just look at what we really mean by these things through the example of product size recommendation, right? And then there are various stakeholders, of course, like the product manager, engineering manager, machine learning scientist. So this is, probably the role that some of us might fit into if we become like, data scientists. Then like there's a data engineer role. So there are many different types of roles. Typically these folks work together, right? Okay. So if I take the first box, which is, or the first circle here, which is like, the problem definition. So what we want to talk about is, how is the customer experience impacted by this problem? Is this problem really important to solve? Is this problem a bottleneck? So the point is, like, a lot of us know how to build models, or a lot of us learn how to build models, but it's important to understand this aspect of product development as well, in order to make sure that the models we are building have a good impact, right? So it's really important to understand from the business problem level, what we are trying to solve. That's what we are trying to say here, right? So these are some things. What is the dollar value of solving this problem? So this is typically something that a product manager answers, but it's good for a data scientist to also know and answer these questions so that they have the right context while building the model. So let's take the example of product size recommendation. So here, what is the customer problem? As a customer, the problem is that it's hard to choose size online. What's the business problem? The business problem is that there are too many size related returns, and they cause, like an impact on so customer experience, and also, it's financially not a great thing, right? If you have too many returns. Okay, so this is the customer and the business problem. Now, how do I know if I have solved the problem? Suppose I develop an ML model. How do I know I solved this problem? So we need to have some metrics. So the success metrics here are, is there an increase in revenue if I actually put this kind of a size recommendation on the website? Is there a reduce in returns? Right? So these are like the two meaningful metrics you can think of here, right? There could be other metrics. Okay, so this is the problem part of it. The next step is like, the data gathering. Then you want to do some exploratory data analysis, literature survey, think of what kind of models you can build, right? And this is the phase where data scientists typically spend, this and the next phase are where data scientists typically spend a lot of their time on, right? So let's take, in this case, data gathering. So what data do we have? So we can have many kinds of data to solve the problem here. So some of the data, like, when I was working on this problem, was like customer transaction data and customer return data. So this was some data that we had, right? So what this means is, what each customer purchased. So for example, customer number, whatever this number, purchased Nike Air Max EU 42 size. And you also have customer return data. What that means is, if a customer actually liked that product, which means it fit them well, they would not return it usually. So that means if the customer did not return it, I would call it a fit. If the customer returned it, then typically the customer is asked to enter, like, whether it is small or large. So if it is a size related return, so then, they will indicate small or large, and I have this return code here. So the data that I have is of the form customer ID, product ID, that is a specific size variant, and whether it is small, fit, or large. Right? So that's one form of data. There could be like other forms of data. There could be like exchange data. There could be like a lot of other forms of data. So taking this data, now I need to sort of understand, I need to do exploratory data analysis on this. Why do I need to do that? So I want to understand, what are some of the challenges working with this data, right? So for instance, some things that we realized in that project was that there are new customers and new products without transactions. So how do we actually deal with that? There is a cold start problem, right? Which is significant. So cold start is typically when you don't have data for like a new customer. That's called the cold start problem, right? Then there's the problem of sparsity, which is that most customers and products have very few purchases. So I'm saying that I want to use this customer transaction data to recommend future size for the customer for future purchases, right? But if the customer does not have any transactions, what do I recommend based on, right? So sparsity is that, if customer has only few transactions, what do I do? So the more transactions the customer has, the more reliably I can recommend. Then the problem of multiple personas, where, so somebody can, so I can buy a size 8 shoe for myself and like a size 4 for my daughter, right? And definitely the online shopping portal is going to be confused what my size is. Then the problem of noisy data, because customers do not always return stuff that does not fit them. And even if they return, they might not say it's because of size. They might give some other reason. So there's all this noise in collecting that data from the customers, right? So there's many issues with the data. And these things you would figure out only when you do the exploratory data analysis typically. So these are the kind of insights that we're trying to draw, and then figure out, what kind of models make sense to build. For example, because I see that, there are multiple personas, I might want to sort of do some form of clustering to build, I want to like sort of separate the two personas of a person maybe. So if I have like, let's say 5 transactions in the past, can I find 2 different personas? Maybe I bought a size 8 and size 7, and then I bought a size 3 and size 4 also. So those 2 transactions, like, belong to one persona, these 2 belong to another persona. So maybe I want to do some clustering. So analyzing the data helps me come up with solution strategies. Okay. So once we actually do this, a good question to ask always is, I know that, we are data scientists, and what we are good at is building ML models, but it's always good to ask the question, can this problem be solved without machine learning? Anirban, is this like can I get like any audience responses? I'm just curious. Hello? Okay. Let me just continue. So we want to
questions.
Yeah, so can I actually ask questions during the session?
Yeah, sure.
Yeah, please.
Okay.
Okay.
Yeah. Okay, so can anyone think of, how you would like solve this problem without using machine learning? Can you think of a simple heuristic solution? Given a product, how do you suggest the right size for the customer based on past transactions? Anyone?
Past transactions, ma'am, need not be a predictor, right? He may not have even purchased this item before.
Yes, he might not have purchased this item, might have purchased like similar items. For example, let's say the customer purchased like 5 shoes 5 times before, right? So this time he wants to purchase a shoe again, different brand. So what could you like, do if you want to give like a rough heuristic what size that person has to?
I will take a wild guess, ma'am. I'm tempted to look at whether we have a customer profile data like an age or something.
Right.
Something to decide on the look at the morphological characteristics of the customer and see whether we can use it.
Sure, that's one thing. But the point is like, is the customer, size, if you're buying shoes, right, is the shoe size correlated with age is the question, right? But nice, you took a guess. Good about that. So what you could do, for instance, is let's say if he purchased like 4 or 5 items in the past, if he or she purchased 4 or 5 shoes in the past, I can just take an average of the size they purchased. Not going to be very accurate maybe, but something, right? Now point is like, is this a good enough model? It's probably not a good model, but that's probably like a starter kind of a thing. So it's always good to think about what is the simplest thing you will do without ML, and maybe you want to build this as a baseline to make sure that whatever you're building, you're spending so much time and effort into is actually making an improvement over something simple. Okay, so what is the simplest machine learning model we can build to solve this project? So that would probably be like another question. So one simple model that I can think of, for instance, is build some kind of a classifier. So like our data is like this. So build some kind of a classifier given a customer and a product. Can I actually predict this label of small, fit, or large, right? And problem is like, that data is pretty sparse and it doesn't work very well. But that's, some kind of a simple baseline I can think of. So it's just an exercise that we are doing here. What are some simple things we can do first, right? Okay, so once you think of how you can solve this problem in a simple way, you want to think about, okay, what are the shortcomings of that and how you can improve, right? So one approach that was used to solve this problem was as follows, right? This was one thing we thought of, where let's say I want to, so at least for things like shoes, right, which have only, if the length of the shoe is pretty much one of the main things that indicates whether a shoe fits me or not. So my foot length and the length of the shoe, right? So can I actually put the customer foot size and let's say the product size on some kind of a latent axis? Can I put them on the same axis so that I can compare apples to apples? So I don't know the true size of the customer, but if I can put if I can find a size for the customer and a size for the product in the same axis, then I can actually say, okay, so suppose, my shoe product has like 4 different sizes, then 4 of them will be like, different points on this axis. And then when a customer comes in, I can see which is closest to that customer foot size and recommend that, right? So in order to do this, so the intuition was that suppose the customer returns saying it is small. So let's say SI is the true size of the customer, TJ is the true size of the product. And if the customer says that the product is small, then SI should be greater than TJ intuitively, right? Customer size is greater than the shoe size if it's small for the customer.
Yes. Yeah.
So SI minus TJ should be greater than some threshold. Then it makes sense for it to be a small transaction. Some threshold B1. Similarly, for large transactions, we would expect the customer size to be less than the product size. So SI minus TJ is less than some threshold, right? And in case of fit transactions, SI minus TJ, we would expect would be, pretty small, right? So SI minus TJ would be like SI should be close to TJ for fit transactions. So it's bounded between some thresholds, B1 and B2, right? So same thing you can see graphically also here. SI minus TJ is like close to 0 for fit transactions, and small is on one side, large is on the other side, right? So this was taking this intuition. Now I have these 3 inequalities. Given these 3 inequalities, right, find the best value of SI and TJ such that these inequalities are, I can write an objective function where these inequalities are satisfied for all the data and find the optimal value of SI and TJ, right? And this was actually published. So this was like, I don't want to go into the details of the modeling here. The reason being, this talk is not so much about the modeling part, right? As it is about understanding how do we know whether this is the right thing to build.
Yeah. Yes.
Okay. So we have come up with this solution. We came up with this loss function, came up with some metric. Then, okay, one of the problems, like, we want to iterate. And one of the problems was that the data is sparse, which means that, so if I have this is a plot that came up during the EDA, which is that if I see how many products have 1 transaction, how many products have 2 transactions, or how many customers have 1 transaction, how many customers have 2 transactions, and so on, I see that for those who have a transaction, most customers have just 1 transaction, right? Which means that I don't have a lot of history for that customer to actually recommend buy. And in this case, like, how do I deal with the situation? So one thought was to, okay, can I use some kind of Bayesian analysis? So I think you already had a session on Bayesian modeling, but just to give like a brief thing, the idea is that, so in Bayesian modeling, you come up with some kind of a prior, which is saying that what is my belief that, so for example, in the shoe case, I would say that the prior is nothing but, let's say, the average size purchased by the customer. So even, and I put, so basically I want a prior for what variable? So I want a prior for this SI and TJ. So the prior for SI would be, okay, what are the transactions by the customer? Can I take the average shoe size? Can I put a Gaussian around it? So that could be a prior. So I come up with these priors, and then I look at the data and try to come up with a posterior distribution that best, which is like, a combination of the prior and the likelihood component, which is coming from the data, right? So in the case of the shoe size example, so I would have something like a prior for both the SI and TJ variables. And then I would, the idea would be, when I find the posterior distribution, which is SI given after seeing the data, what do I think for that of that SI? After seeing the data, what is the distribution for TJ? That's the posterior distribution. I can make better estimates because I will also know how certain I am about a particular SI and TJ. So when I find a posterior distribution, if the variance is high, then it means I'm not so confident. But if the posterior distribution is peaked, let's say the posterior distribution is peaked, then with low variance, then I'm more confident. So it is a way for me to come up with whether I'm confident about my predictions or not, alongside just predicting stuff, right? That's the whole idea. And then we actually came up with, a model for Bayesian recommendation, which is, so if I actually fix TJ and, draw this distribution for SI, I want it to be at close to TJ for like peak at TJ for fit transactions. The distribution, the PDF for SI is going to the right for, small transactions and to the left for large transactions, because, we expect SI to be less than TJ for large transactions. Right. So this is the intuition when I look at, Bayesian modeling for this. And again, we come up with a generative model. And so whatever I just described, that's the PDF here, you see, for small, fit, and large. So this generative model, and then, okay, we make some predictions based on this, right? So this is a model that is there and we make some predictions. Okay, so the point is now we have this model. We need to, the next step is really, so now we thought of how to build the model. We have a few options. We've thought of, what is the simplest model without ML? What is simplest model using, like maybe a classifier? Then we thought about this technique. Now we need to assess, how hard it is to actually build this model. For example, when I'm actually thinking of this model, I'm thinking of more like, an inference formula. But then if I have to implement that at scale, what kind of technology do I need to use, right? Which becomes very important. So if I have like millions of transactions, like how much, what is the memory requirement? Do I need to have some kind of distributed processing, right? So these kind of questions would become important to answer. So, so that's something that we'll focus on in, the model and data pipeline development. And following that, we would need to evaluate the model. So we'll come to that part. So in the case of this product size recommendation, it so turned out that the Bayesian model could actually nicely fit into memory, and we could implement it in Python 2.7, because we were doing it on, in this case, you might need to build different models for different categories, for instance, right? And for a certain category, we could actually just fit it in memory. But for the previous algorithm that I talked about, which was not Bayesian, actually that required more memory, and that also required more computation, and maybe it might need to be distributed, right? So you need to figure out like, what kind of environment you will use. So in this case, this was just Python, and memory requirement was less than 10 GB. And what is the runtime? What is the inference time? So you would ask all these questions. What kind of hardware you want to use? So these are some questions that you will answer in this phase, right? And typically, as you all know, so when we build a machine learning model, there is the training time and the inference time. Both of these are important. And sometimes, you can take more time to train a model, but the inference may be very time sensitive. In that case, you need to make sure that, you need to measure your inference time and see if it's under the required SLA, right? Okay. So once you figure out how to build a model, it's important to measure the right metrics, right? So the basic metrics that I can think of are some kind of, I can treat this as, so the way I make the prediction in this particular use case is, once I have a value for SI and TJ that I figured out using my model, I will see which of the child sizes or which of the size variants for the product is closest to the customer size. And then based on that, I would predict small, fit, or large, right? So I can actually just treat this as a classification. I can use classification metrics on this problem. So what we typically used was like AUC, right? And while I can use this metric, so this is, so as data scientists, right, when we are asked about metrics, the metrics that we think about are like AUC, F1 score, precision, recall, RMSE, these kind of metrics, right? So, but what you also need to think about when you want to, when you're actually in industry and you're trying to build a product, is to understand not just the ML metric that you're going to measure, but so in this case, I can think of this as an ML metric that I will use for maybe like my hyperparameter tuning and things like that, a problem level metric, and a business level metric. So we already said that the business level success metric is to either reduce returns or to increase revenue, right? Now, what is this problem level metric? This is something that's connecting these two. So I want to say that, in my case, I want to measure the accuracy and the coverage. So what I mean by this is, if I actually, it's good to give a recommendation, but if I think it's better to give some recommendation than none, and I just give a recommendation for all products, that could be like a really bad thing, right? Because if I give a wrong recommendation, somebody might end up buying the wrong size because of me, and the number of returns might actually increase instead of decrease, right? So my goal here is not to give a recommendation for every product. That's not my goal. My goal is to reduce the number of returns, right? We need to be very clear about the distinction. So hence what we want to measure here is accuracy. So this is something like precision. So basically, how many of the times that you recommended the right size, right? That's accuracy. And coverage is how many, what portion of your customers could you actually recommend something. So if you're not confident, you're not recommending to some of the customers, right? So what percentage could you actually make a recommendation? So these are two metrics. This is like a little bit like precision and recall. But the point is, we want to make sure, like, which of them is more important for me, right? So in this case, even if I show it for fewer people, it's fine. But I want to make sure that I show the right thing when I do show, right? So in my case, precision is more sort of important in this particular problem. And it's extremely important to be aware of that when you're building a model and not just go by the AUC, right? So so that's about the offline evaluation. And often, this business metrics are hard to often measure in an offline fashion, whether it will increase revenue or reduce returns. But typically we do try to simulate get some kind of a simulation metric to see, okay, what would have happened if they bought this kind of a thing. So we try to sort of simulate that in some cases, but sometimes this is harder to measure unless we actually do live testing. The reason being, sometimes it's not just the solution, but maybe even the way the solution is presented, or there are some other aspects that might actually impact how your model is finally going to impact customers. So it's always important to do live testing. So in theory, there's no difference between theory and practice, but while in practice there is. So live testing is typically, one way to do it is to do A/B testing. All of you might have heard of this before. So the idea is that you want to have this for, feature or whatever model that you're, this recommendation feature for a certain subset of your customers, and then figure out if it has a positive impact or not. So I'm not going into the details of how to do A/B testing, but the idea is that, okay, you actually roll it out for a small segment of your population, and then there is a control group where this is not happening. And then you try to see, what impact your change has, right? So these are typically the steps. And then finally, you were going to roll out the model if it works well. So if you get good results in live testing, if you find that, you will measure your success metrics. So if you're looking at returns, for example, sometimes it might take a long time to actually get that data. So returns maybe happen, you get the data only like 2 months or something, if there's a time window for return, for example, right? So you have to wait for 2 months to see how many returns happened after your live test, right? So once you actually do all this and then you figure out that, okay, it is having a positive impact, how much ever impact I want, then you would decide to actually roll it out. And when you say roll it out, this might be like, okay, how do I roll it to different products? I did this for one product. Now, can I do it for other products? Can I actually, other product categories? Or I did it for one geography or one country. Can I do it for other countries? Right? So these are the kind of things that would go on in the next step. And finally, you would actually do the ops and maintenance part, and you might want to set up some alarms and monitoring and things like that to make sure that if something goes wrong, immediately someone can take action there, right? Then you might also, sorry, go on.
Can I ask a question?
Yeah, sure, you can ask.
Yeah. In the model, when after you're rolled out, let's say you're rolled out for multiple products or multiple views, when do you start tweaking the model? Because it doesn't stay permanent, right? You still need to evaluate another thing. What are the clues or what are the signals, symptoms you look for, which tells you that, oh, no, it's time to re-examine the model? Is it something?
Right. So you need to come up with these metrics typically. So in this case, maybe you want to have as a part of your pipeline, you might want to always keep constantly evaluating some metrics that you decide. So in this case, it could be like a combination of the ML metrics and the problem metrics that you talked about. So
right.
you want to keep like whenever, so this typically the model will get trained on a constant basis, right? At least in this case, the model had to be trained on a constant basis. And you will be getting fresh data, let's say on a monthly basis, maybe, or maybe a weekly basis here, and then retraining the model, right?
Correct.
So you need to choose a cadence depending on how fast you think the data is going to change. And then once you set a cadence, you, as a part of your pipeline, as soon as you train the model, you will probably do some kind of train test split there, or cross validation there, right?
Got it. Yeah.
First you will do hyperparameter tuning, then you'll do it you will actually try to compute on some test set what is the metric. And when you do that, you want to actually make sure that you compute all these metrics here, right? So your ML algorithm metrics, your problem level metrics, right? And if you can simulate, you can try to simulate how many returns maybe in some sense. So if you recommended something and that is so you actually have the label of small, fit, and large, right? So if you recommended correctly using your algorithm, then there's no return, you can say. If you did not recommend correctly, you can consider it a return maybe, and you can sort of come up with some metric, offline metric, on how many returns are there, right? Yeah. So you need to sort of keep ideally you would need to keep evaluating these metrics and dumping them somewhere, so that if you see that there is something wrong with any of the metrics, just like you monitor the health of a machine, right? You want to monitor the health of your models, and you want to see if any metric is below the threshold, or is not within the threshold that you want. You might want to see why.
Thank you.
Similarly, data sanity metrics also you might want to come up with for the data itself, right? So if the number of missing items is higher than this for a certain column, you might come up with some metrics, because you might be ignoring all rows with missing data, suppose, let's say, in some in some data set. Now, if that is too many, then you might not want to do the same thing. So you might want to have some sanity metrics, right? So it could be, it's not just based on the ML model, but also the data sanity metrics. So typically you want to constantly evaluate these metrics ideally and dump them somewhere as a part of the pipeline.
So there is a question in the chat, if you can take a look.
Okay. Sorry, how do I, hold on. Okay, can anyone actually read out the question?
Hello. Yeah.
Yeah. Okay. I
How
got it.
do business level metrics and product level metrics differ in the context of any scalable ML product?
Okay. Yeah. So the reason I put them as business level metrics and product level metrics is because business metrics, like let's say my business metric is increasing revenue, right? It's not very easy to measure it while I am prototyping and building this model, right? Because unless I actually roll it out and I have to see how it is, maybe when I roll it out, there are so it's hard to measure the business impact directly when I'm actually building the model, right? Like I said, the UI might make a difference, or there might be like something else in the page that's distracting the customer. So there are a lot of things that go into picture when and the only way to get the business metric is typically by actually doing some live testing. But the reason I talked about these product level metrics is because I don't want to wait until I roll some, like until I do live testing, right? Because live testing itself is actually an expensive operation usually. So I don't want to wait until I do live testing to see whether it might have a possible business impact. So this problem level metrics that we talked about are something like an in-between, where I'm thinking what are the metrics that I measure that can actually be more reflective of the business metrics, right? So AUC F1 is one thing, one level of metrics that we think of as data scientists. But can I think of, more metrics that associate more closely with the problem, like this in this case, accuracy and coverage, right? And these are something I can communicate with. Suppose I communicate about accuracy and coverage to my product manager, they might be able to connect with it better. But if I tell them AUC is good or bad, it does not maybe tell them a lot about the business impact directly. Is that, does it answer to some extent?
Yes, ma'am.
Okay. Yeah. So that's the whole idea. Come up with these different layers of metrics so that just don't go by your standard ML metrics. So, and this happens very often. In fact, this is one of the main challenges that I've seen every time I work with a team. People do get stuck in ML metrics and don't come up with problem metrics sometimes, right? Okay. Cool. So this was what we saw, the machine learning project development lifecycle. So if I just want to summarize this very quickly, the takeaways here would be, building products using ML is a very iterative process. So as we saw here, I did not talk a lot about the iteration process because I wanted to sort of condense this a little bit. But the point is, there is this question between every two steps. So basically, do I need ML? If I need ML, I'll go here. Then I'll do feasibility impact analysis. Suppose I decide that, either the impact is going to be low, or if it is going to take too much time, I might go back and refine my problem. If there is a simpler thing I can solve with what I have, with the data I have, for instance, right? If not, I might need to go collect more data. So it's always a very iterative process. So even after I build the model and test the model, then I go back and see, if it's not having the impact that I want, I might go back and see, okay, this is what I've already invested it and built. So what can I do with it? That's one way of thinking about it. Or I might have to, if the problem definition is not fully solved, I might need to ideally iterate and come back and do something else. So it's like a very iterative process overall, right? And every time, this box here is saying whether it will go to the next step. It's like a gate, whether it will go to the next step or it will go somewhere else. Okay, so it's a very iterative process. And second thing is, make models for products as simple as possible, but no simpler, right? So we as data scientists always want to make the most interesting model. And I mean, believe it or not, it's sort of built into all of us. We want to build interesting models. But from a business perspective, it's always useful to build simple models that work well. So if you can build a simpler model that works as well, it's easier to maintain it in the long run, and there are a lot of advantages there, right? You won't be spending so much time on it, and you will realize that gain sooner. So we want to make things as simple as possible, but no simpler, of course. And if we can make a better model, and that will actually lead to some improvements, we want to do that, of course. And there's a trade-off there. To create real impact, it's important to measure the right metrics. So this is what we talked about. We need to know, for instance, whether precision is important or recall is important. It's extremely important to know that, right? And there are many times this would come and bite us if we don't figure this out correctly. Okay, so this was the first part. Any questions on this part so far?
No, ma'am. I think it's good.
Okay, so this was the first part. Now we'll go to, the second part of the talk, which is how do we build fair and unbiased ML models? So there is the fair part, and then there's the unbiased part. So, okay, let's do this. So this is a part of, taking models to products as well, because when you're doing your EDA, when you're building your model, we need to be aware of the kind of biases that creep into our ML pipelines in order to be able to handle that and build models that make sense, right? So that's the reason we have this sort of ties in with the first part as well. And we want to sort of dig deeper into this aspect in the second part. Okay, so let's start with understanding biases that creep into ML models. Let's take an example. So let's say it's like a simplistic example. Somebody is building an application, building an ML pipeline to score job applications, like resumes, let's say, right? Some kind of a resume processing application. It takes as input qualification, major, it extracts all these fields from the resume, let's say. Years of experience, keywords from resume, maybe zip code, gender, and age, right? And then it's trying to figure out, score the resume, give a score to the resume, whether to take it to the next step or not. Like, because there are, too many resumes maybe, and some kind of a pre-screening thing. Now, can somebody tell me, like, what could go wrong with this? Looking at these features that are there.
Might overpower other, like qualification or year of experience. Like someone have a good qualification over the experience, then that candidate should be considered over someone with not that so good qualification over the experience.
Okay. Yeah. So if the qualification and experience is good, they should be given more weightage, you're saying, right? Is that what you're saying?
Yes.
Okay, that's true. Yeah, we want that. But think about what would happen if, suppose zip code, suppose I'm building some kind of a small regression model, let's say. And one of my features is the zip code, right? And it might be that very few people from a certain zip code got selected for, in that company earlier, let's say. Our model might actually end up learning that everybody from that zip code has a lower probability of getting selected, right? That's not a good thing, because or take something simpler, like let's take gender. Gender actually is a one of the features here, right? So it might just think that if there are at the moment, let's say there are fewer female employees in a company, right? Then it might actually end up thinking that the algorithm might actually learn that the probability of getting selected is lower if you're a female. That's not what we want, right? So this is an example of a biased model. So there can be different ways biases can creep into our ML pipeline, right? And we are going to see sometimes it is in the data, sometimes it's in the way we are building the model. It can creep in at different places, and we will try to see, what are some of the ways these biases come up. And in the second part, I will actually focus a little bit more on societal biases and fairness. So there are many kinds of biases, and not everything is related to fairness necessarily, right? For example, you have inductive bias, which is, you'd have seen like, your regularization in when you have like a regression or a classification problem, right? Regularizer, like your ridge regularizer, whatever. So that's also a form of bias where you're, so by definition, a bias is something that leads to a different outcome, right? So basically, even if you put a regularizer, that's one form of bias. But there are lots of, that's not the kind of bias we are talking about here. So we are talking about, so there are lots of other forms of biases, right? If you see, there's like a big list of biases that you can find if you look for biases online, right? So biases can come up in for many different reasons. So what we will do is we will look at one example. Okay, so there's we'll take one example called Simpson's paradox, which is in this big list here, and we will actually start with that and then move over to some other forms of biases. Okay, so let's look at this example. This is the example of the UC Berkeley gender bias example, where this is the applications received at UC Berkeley in 1973. So if you can see this table, we see that if you look at the number of men, percentage of men and percentage of women that got admitted, we see that 44% of men got admitted versus 35% who got admitted were women. So it looks like probably a male applicant had a slightly better chance of getting admitted. But if you take the top few departments, top 6 departments, and you see individually per department, what percentage of women who applied got admitted and what percentage of men who applied got admitted, we see that in most departments, the percentage of women who got admitted was higher than the percentage of men who got admitted. Even though if we see overall, the percentage of men who got admitted is higher, right? You see the paradox, right? So basically it looks like the percentage of men who got admitted is higher, but individual department wise, if you see in more departments, women, there's like a higher percentage of women who got admitted. So now why is this so? So it's possible that women, there a lot of women applied to those departments which were very selective. So for instance, the acceptance rate is pretty low in this department compared to like some others, but the number of applications, if you see, like 593 women applied versus only 325 men, right? And because the acceptance rate in this department is low, it feels like a lot of women who applied overall got rejected. So this is an example. Now let's just put this in simpler terms and see what's happening mathematically underneath this. So let's say you have, these two groups, group 1 and group 2, right? And these could be like, the different departments here, and your A and B could be like male and female. So if you have this ratio A1, small a1 by capital A1 greater than small b1 by capital B1, and you have small a2 by capital A2 greater than small b2 by capital B2. Now suppose you add the numerators and add the denominators and take the ratio. So we would intuitively think that A1 plus small a2 by capital A1 plus capital A2 will also be greater than small b1 plus small b2 by capital B1 plus capital B2, given these two inequalities. But the fact is, it might sometimes be less. So let's look at this example. So in the first group, in group 1, let's say small a1 is 18, capital A1 is 19. 18 by 19 is greater than 19 by 20. Then the second group, let's say we have 80 by 400. This is nothing but 20 by 100, right? So 80 by 400, 20 by 100 is greater than 19 by 100. But if you add up the numerators and denominators here, 98 by 419 is actually less than 38 by 120, right? So aggregate behavior could be different from behavior in individual groups. So there's another popular example for this, like the kidney stone treatment example, where you can see the ratios here. So you have like small stones and large stones, and there are 2 types of treatments. Now it turns out that both in treatment A works better both for small stones and large stones when you look at both of them individually. But overall, if you see, treatment B actually turns out to be giving a better ratio of successes. So this is like, this number here is what percentage of cases that were treated with that treatment succeeded. So 83% succeeded with treatment B overall. But if you look at small stones and large stones independently, 93 and 73% succeeded respectively, which is more than what happened in group 2, right? And this is exactly the same example here. And maybe you can explain this by saying that possibly, treatment A was only being applied to, was better, treatment A is probably better, and hence it's being only applied to large stones where, which are harder to treat maybe. And maybe, like, if you couple that with the fact that most of the small stones are easier to treat, so it almost always succeeds. If you couple these 2 facts, you can intuitively see, like, why this kind of a paradox is occurring. Even otherwise, you can just see this ratio, why this paradox is occurring, right? And, another simple example is like, if you see, so if you look at correlation within subgroups, right? So I have like 3 subgroups of data here. Let's say like they belong to different time periods. So if I want to see the trend in this data, if I were to plot a line to summarize this data, it would be like a straight line with a positive slope. But if I see each individual group, the data actually has a negative correlation between both the X and Y variables, right? So if I were to summarize this with a line, I would see like a line with a positive slope, but within each group, I have a line with a negative slope, right? So I might end up saying that these 2 variables are positively correlated if I just look at the aggregate picture, but group wise, if I see, they're negatively correlated. Example of this is, which comes up in economics, for instance, is demand and price are negatively correlated, right? So if price increases, we would expect demand to decrease. But there might be some reason, external reason, over a period of time why both demand and price are increasing, right? So if I look at a different time period, overall the values are higher, but again, at the micro level, you can see this negative correlation. So this is an example of Simpson's paradox. So what about all this? Like, what does this mean? Okay, we looked at Simpson's paradox. What about it, right? What this means is, this is one kind of problem that could creep in where subgroups behave differently compared to aggregate. So if you think that your data has this kind of a problem, right? It might make sense to make predictions at a local level. So you might want to build a different model for each of these subgroups, right? Instead of building like, this overall straight line. But what that means is it's important for you to detect that this kind of a problem exists first, right? So this is one kind of a problem that could creep into your ML pipeline. Now, we won't spend so much time on all the others, but let's see, what are some other ways in which we can end up with biases in ML pipelines. We'll look at a few of them, like specification bias, sampling bias, measurement bias, annotator bias, and inherited bias from other ML models. So we'll look at these. There could be many others. So specification bias is something that arises when we use bad features. For example, in the resume scoring application, it was not a great idea maybe to use the gender or age as a feature maybe, right? So you saw what could happen because of that. So it's important. So specification bias is that which arises because of the way we designed our model. So that means the inputs to the model, or the way that we design our loss function itself. So if our design is, including some of these sensitive variables sometimes, for instance, like the gender we talked about, it could lead to bad models. So examples of such variables are like gender, race, age, and so on, right? And sometimes even if we actually do not use these features directly, we might end up using proxies to these features. So for example, if we go back to the resume application, we use zip code as a feature. It's possible that certain ethnic groups are residing more in certain zip codes, right? And we might like inadvertently be saying that certain ethnic groups are less likely to get the job if we actually put maybe zip code as a feature, right? So we need to be cognizant of, even if we don't include that particular sensitive variable, there might be other proxies that are highly correlated with that sensitive variable, which are probably not really required in this scoring application as a feature. But since we are putting that, we are inherently like, inadvertently getting that bias in. Okay. So that's specification bias, which is from the model design perspective. Next is sampling bias and, selection bias, and combining this. So this could happen when you're not adequately sampling from all subgroups. So for example, let's say that you have very few resumes from the major information systems, right? And you have a lot of resumes that are actually coming from like, something like computer science. Does not mean that probably, it might just be like a naming thing, right? But so in this case, it does not mean that someone with information systems is, less likely to get a job. Or take something like electronics. There might be fewer candidates who are coming from like an electronics major compared to like, let's say, computer science major. That does not mean that, someone from an electronics background will be less suitable for a job. So sometimes the job might require a certain background, but in many cases, if it does not, like having not having enough samples from those particular subgroups could actually lead to some kind of a bias, the system thinking that the probability of getting selected is higher if you're from a certain group, right? So for example, if you have more male resumes than female who got accepted earlier, then it might just think that the probability of it is just more likely to get accepted if you're a male. So it's important to sample adequate number from each subgroup. Okay, so next is measurement bias. So this is not recording the measurements correctly. So an example could be like, error in noting down survey responses. Someone comes to your house and does a survey, right? And then suppose enters stuff wrong. That's an example of measurement bias. Or it could be like, some sensor going faulty. Or it could even be like, bad design of UI in forms. For example, you could, if you actually, let's say you have this form where you're asked about your COVID symptoms to understand, suppose somebody is trying to collect data in order to analyze your data and come up with some insights that could help with, some kind of COVID analysis. You have these three things: high fever, low fever, no fever. But there is no option for I don't remember. Suppose somebody else is filling this form, right? Not the patient themselves. And because there is no option of I don't remember, they'll end up filling garbage, right? So you'll end up getting garbage. So it's very important to design your input equipment or, whatever form that you're using correctly in order to get meaningful data, right? So this is an example of measurement bias. Then there's annotator or label bias. So this is an example where, so basically there are two things that can happen here. So one is you might be using an annotator, and annotator might, make a mistake, or annotator might have their own biases when they're labeling something. Or there could also be human biases that creep in from biased decisions in the real world. For example, suppose there is like, Suppose in a company there is an interviewer who is biased, thinking that certain majors are better or certain institutions like deserve more credit, right? Then the label data that you get to train your model will have those biases encoded, because if you see the successful candidates, they will be from those groups, right? So that bias will inherently creep into your model because you're training with data that is inherently biased, right? So that's annotator or label bias, right? And then there could also be inherited biases from other ML models. For example, the input to one ML model could be coming as an output from another ML model. A typical example is word embeddings. So you use word embeddings as features in a lot of NLP tasks. But you might have heard that, sometimes there could be biases creeping into word embeddings. For instance, there's this paper, Man to Computer Programmer as Woman to Homemaker, that shows that, word embeddings also have inherent biases. And if you used a biased model, your application could give biased outcomes. Okay, so we talked about different kinds of biases, right? And not all of them necessarily relate to fairness. So fairness is something is a slightly different concept, where we want to do what makes sense as the right outcome from a society perspective, when we say we want a fair outcome. So let's understand like what we mean here. So typically we refer to societal biases that creep into ML models based on some of these sensitive variables when we talk about fairness. For instance, race, color, national origin, religion, familial status, marital status, so on. So when you or age, so some of these features. So let's take another example, right? So suppose you are actually building a model for loan eligibility, and you actually have gender as one of the features in your model, right, which predicts whether you're eligible for a loan or not. Suppose, let's say, previously very few women qualified for a loan, maybe because most of those women had lower income, or it could even be because of a biased person who's evaluating, right? We don't know, but it could just be because of many women have lower income. Uh, so the algorithm is likely to learn that women are less likely to qualify for a loan. It could also be the fact that there are in general fewer female applicants in the pool. Maybe we sampled more, there are more males than females in the data set. That's also possible, right? But bottom line is, algorithm might learn that women are less likely to qualify for a loan. And suppose a female CEO of an MNC applies for a loan and the algorithm denies the loan. This is clearly not what is intended in this case, right? So this is an example of how this outcome is not fair, right? And what do we do about this? So basically, how do we make sure that this does not happen, right? So how do we measure fairness? So so we want to understand first what societal biases that we care about for an application. So for example, in this case, let's say we are talking about fairness from a gender perspective, or it could be from a ethnic group perspective, right? Or it could be based on age or one of these sensitive variables, right? And what we do, the kind of metrics we use for fairness also depends on the kind of task that we're using. So let's say we are doing like classification. So so it would be slightly different. How we measure fairness will depend on what kind of task, classification, regression, or clustering, for instance, right? And let's take like an example of classification. So typically we have this confusion matrix of like true positives, false positives, false negatives, and true negatives. So the first thing you need to do is to understand what your sensitive variables are. In this case, gender and race, let's say, right? Or let's say gender, right? So you need to make sure that typically some things that are used, at least for classification, to measure fairness are equal opportunity, which means if I take the example of the resume selection, right? A good candidate, irrespective of gender, should get selected for a job, right? What this means is, if I go back to the confusion matrix, I want of all positives, of all people who are eligible for the job, how many actually got selected, right? So of all people who are suitable and good for the job, how many actually made it through, right? That is the true positive rate, or it's the recall, right? And what we want is that this should be roughly the same across different groups. Is this the same for, like, different gender groups, or is this the same for different racial groups and so on? The next is equalized odds, which says that if I'm a good candidate, I want to get selected irrespective of gender. So I should have equal probability of getting selected irrespective of which group I am. Plus, assuming I'm a bad candidate, do I have the same chance of making it irrespective of gender? So here what we would measure is, out of all negatives, how many were falsely classified as positive? This should be similar across different groups as well, right? So we look at both the TPR and FPR. And another common metric is like demographic parity, which says that the likelihood of being classified is same for protected versus non-protected groups, right? So the basic strategy here, and if we go to regression, right, we would again come up with some metrics like RMSE or any other metric, and say that for different groups, we have roughly the same metric, right? The metric should be within some threshold. Is a way we can we can check, if the relationships are very different for different groups, maybe there's a problem. So that's like, basic way of checking. And again, there's like demographic parity for regression also. So the point is, like, how to what changes can we make to the ML pipeline to handle fairness?
Hello?
Hello?
Yeah, there is a question.
Sure.
Like mitigating demographic biases in ML model, say recommender system, usually bring in the concept of fair treatment among all the groups. But this might also affect the personalization aspect. Can we improve bias as well as make our model personalized?
Could you repeat that?
Yeah.
So why do you think it impacts the personalization aspect?
Yes, like mitigating demographic biases in ML model, say like recommender system, usually bring in the concept of fair treatment among all the groups. But this might also affect the personalization aspect.
So when you say affect the personalization aspect, so you're actually, what kind of recommender are you building here?
Kirandeep, can you unmute yourself and ask your question?
Am I audible?
Yeah.
So here I was considering a simple example of a recommender system. Suppose it is recommending some products online. Let us say some shopping elements. So suppose like if I try to bring in the fairness concept, and let us say we are saying that males and females should be treated almost equally, since it is like a demographic bias we are targeting. Now, if the males are getting the advertisements of some jobs, then similar kind of recommendations or advertisements are presented to the females also. And similarly, in the in a concept of shopping, that suppose like males are getting more recommendations of shoes, and females also are getting now the elements like the recommendations of shoes only. Now, if I say, however, females are actually more interested in the like makeup products or something like that. So now the females will not be getting to very personalized recommendations, but rather they will be getting recommendations according to a fair treatment. So how can we tackle the concept of a fair model which is also personalized?
Okay. Okay, I understand your question now. Okay, so basically when you're talking about fairness, right, it is not unfair to, so basically there is a trade-off here, right? So first, let us say that whenever you're talking about fairness, it will typically impact the overall metric that you're trying to see. For example, the overall RMSE, whatever parameters you get when you try to reduce the RMSE overall, will be different from the parameters that you get if you try to make sure that, you know, the RMSE is low plus it is roughly equal across groups, right? So it might not be the overall optimal solution, right? That's one thing to keep in mind first. Second thing is, in this case, it might not be like, you know, women are actually browsing more things of a certain kind. It might be okay to, you know, sort of, you want to take a balance there. You might be okay to actually show things that they're buying as well, right? So so basically, I think there is like a trade-off there, and you could actually, if you try to incorporate, so where you incorporate fairness is one thing, whether you want to incorporate fairness in a problem like this. But even if you do, to some extent, you want to make sure that women are not shown only certain kinds of products. You could actually sort of use a combination of things to populate the feed, for example, right? Typically in recommender systems, people do use solutions where you use a combination of algorithms to populate the feed. For example, you want to like have this trade-off between uh, recent items versus or you want to make sure of novelty sometimes, so that they don't see only things that they usually see. So there's always the concept of, you know, trying to mix that feed. So you can go for solutions like that, right?
So, like, if we choose some algorithm which also, along with maintaining fairness, which also brings in the concept of diversity in the recommendation lists, so that could be one possible solution.
Yes, so you want to recommend what other women see, maybe, I mean, one possible solution. And then you also want to make sure you can actually have, like, you know, come up with your fair solution and show that together, or like, you know, yeah.
Yes.
Similar to the way you handle diversity.
Okay, thank you so much, ma'am.
Again, there could be like many answers to this, but that's one thing I can think of. And you want to also think about where you want to incorporate this fairness. Like, you know, in some cases, it might make sense to put in that fairness. In some cases, it might not. So that's actually pretty important. What problem you want to, you know, use it in, right? Okay. So approaches to handle fairness at a high level: pre-processing or fixing the data sometimes. So for example, if you have sensitive features, you might want to like remove them if they are not important for your outcome, like that gender we saw in certain cases, and you know, whatever sensitive attributes. Remove features correlated with sensitive features, like proxy features, whenever you can, right? Sometimes it's not possible to remove the features because these features may actually be important and indicative, but where you can, you want to remove these. You might want to change the distribution of sensitive variables. For instance, collect appropriate data from all subgroups, right? This is something we've seen in process. So sometimes you can actually build fair models. There's been a fair bit of work on changing the objective function to incorporate fairness. One example is like, you know, you can have these constraints such that subgroups have the same like like the same RMSE, for instance, right? So that can be incorporated into the objective function, right? That's one way of handling it. But another way is to post-process, which is sometimes you might want to use a different threshold for each group if you know that there is a systemic bias that's leading to unfair outcomes, right? For example, you might have, like, if you're using like logistic regression, so you have a threshold for cutoff, you might have like a different cutoff for different groups if you want to ensure certain outcomes. Or you might implement a fair decision-making algorithm on top of the model output. So for example is like debiasing word embeddings. So if you are just seeing how, so I'm just seeing how much more time we have actually.
10 minutes.
Okay, just 10 minutes more, right? Okay, cool.
Yes.
Okay, so another example could be like, debiasing word embeddings. So I'll just briefly go over this example. So this is one way of, example of post-processing to remove bias. So this paper is pretty popular, Man to Computer Programmer as Women to Homemaker, which appeared in NIPS 2016. And all of you probably know about word embeddings that we use commonly in NLP tasks. The idea is that vectors of similar words are close geometrically. And we also have the nice feature that vector arithmetic captures relationship between words, right? Like man minus woman would be close to king minus queen, for instance. And we can come up with these nice analogies. Paris to France as Tokyo to what? And using this relationship, we can actually find out, Japan. So it also happens that these embeddings often have some gender stereotypes, and they generate analogies like this: she to sewing as he to carpentry, man to woman as programmer to homemaker. So, or man to computer programming is woman to homemaker, right? So other examples are, you know he to she. Other examples are she to he as housewife to shopkeeper, right? Which is not a great analogy, because we can have shopkeepers who are women, right? Similarly, she to he as nurse to surgeon, right? This is not a great analogy to have, because you can have nurses who are men and surgeons who are women and so on. There are some analogies which are appropriate though. For example, she to he as mother to father is appropriate, because mother is intrinsically a she and father is intrinsically a he, right? So so this paper talks about how to debias these embeddings. So it talks about, like, there are two types of biases, direct and indirect bias. But the point is, what happens when you have these biased embeddings? One example could be, so if you search for like CMU computer science PhD students, you'll have you might end up seeing more male profiles because of your analogy of man to computer programmer as woman to homemaker, right? If you have that kind of a property for the embeddings. So one of the things that this paper does, for example, just to give you an example, is to debias the embeddings by finding something like a gender subspace. So it takes the difference of all the gender specific pairs. So for example, she and he are a gender specific pair, as will be mother and father, for instance, right? So it would take all these gender specific pairs, take the difference, and of all these vectors, take the principal component and call it a basically that is the gender subspace. In this case, if you take one principal component, it's like the gender direction, right? And then try to remove this direction from all embeddings, right? That's one thing you can do. That's an example of the kind of post-processing you can do, for instance, right? Right, so that's this paper basically, right? So I'm going to leave out the other details, but this is an example of post-processing. Okay, so what are some practical considerations now? So when I'm thinking about designing ML pipelines, the first thing is to identify the right sensitive variables that I care about in this particular application, right? And that everything that follows depends on this. So for example, suppose I have an application to predict health insurance premium. So is age a sensitive variable? No, because age is important to predict the health insurance, right? Is gender a sensitive variable? No, because males and females have, like, different kinds of probably some health problems are different, and different they have different anatomies, right? Is location a sensitive variable? Probably yes, because my zip code should not determine whether I get the insurance or not. Is salary a sensitive variable? So if I'm able to pay the premium, maybe if I pay the premium upfront, it should not matter whether my salary is high or low. So salary need not be considered really, right? If I'm going to pay it upfront. So it is a sensitive variable. So depending on the application, so another example is, like, suppose you're predicting marathon completion times, right? marathon is like, a running event, running 42 kilometers, how fast one can run. Is age a sensitive variable? Yes, because older people run slower. It is a fact. Is gender a sensitive variable? Yes. Men are faster than women. It's a fact. Is location a sensitive variable? Sorry, so is age and gender are not sensitive variables because they are important for this prediction. Is location a sensitive variable? Probably not here, because if you're in a cold place, maybe the completion time will be faster. If you're in a hot place and you're sweating a lot, the completion time might be lower. Is salary a sensitive variable? Obviously, yes, because the salary should not really matter for marathon completion time, right? So you should, in a lot of cases, you might need to use your common sense to make sure you're using the right variables. And if you think sometimes it's okay to add this other variable, it will not harm me, it might actually end up harming you because it will introduce some bias maybe, right? Okay, so a few other considerations. Sometimes not including a feature could also result in a bias, right? So for example, if you remove gender from marathon prediction time, you'll get like a really bad model where men and women are given some average time, which doesn't work for either, right? So sometimes you can't remove a feature. Sometimes a fair solution is not optimal in another sense. We already talked about this, right? And finally, like, measure fairness on an ongoing basis. It could be part of your automated test suite. And one last point on fairness is when to model fairness. We talked about this a little bit, and we can't use the same strategy everywhere. So for instance, there's this concept of world as it is versus the world as it should be, right? So if you are building an app that tells you the probability that your loan will be approved by a bank, you want it to reflect all the biases that the bank might have actually. You don't want it to give you an idealized answer, right? But if you are building an application for the bank to predict whether to decide whether to approve a loan or not, then you want it to be fair. You want to consider fairness there. You want to model the world as it should be, right? So there's that aspect as well, when to use fairness and when it does not make sense to use fairness, right? That partly, also applies to the e-commerce example that came up earlier. Okay, I think about for the fairness thing, I think there are like also like a bunch of pieces of software and articles that you can actually look up that most of the big companies have. So there's like one from LinkedIn, Google, and you can actually go and take a look at these. Right? Okay, I think I'm on time. Any questions? Any questions, anyone?
So there's a question in the chat that I don't know, you might have already tackled.
Okay, let me check.
That's about the personalization versus.
I think that's already asked. Yeah.
Got it. Thank you.
Yeah.
In general, so in general, see, we always the more, I mean, the approach has been to look at fairness as a sort of added constraint, right? On the model that it should.
So yeah, actually you can. So that's actually one of the things that I did mention was that you can do it in 3 different ways, like pre-processing, or you can put it in the model, or you can do post-processing. So adding it as a model constraint is ideal. So if you have the time and effort to formulate a new model, you can actually add the constraint into the model, right? In many cases.
But I wasn't really asking that. I was asking, I mean, that you covered, thank you. What I was asking is that there is this sense that once you add it as a constraint or you do it in the pre-processing, that there is this trade-off that you are doing, right? That yes, we are making the model fair, which is ethically the right thing to do, but it's possible that you're losing efficiency.
Yes,
It's
exactly.
possible you're losing
Exactly.
predictive accuracy. Is that always the story? That's my question.
I think
Right?
in many cases it is the story, right? So usually when you actually optimize for fairness, you will not be like getting the overall optimal solution that you consider when you consider like, the entire, it is always a trade-off. And I think it's partly the what you want as a company to have. That's one thing, like company culture is one thing. And yeah, and the second is, yeah, maybe you want to actually then consider the trade-off and do some kind of a combination approach. I don't know, have you actually encountered other ways, like
Yeah, my point is, my position is that we perhaps think that it comes up as a trade-off because we are looking at only short-term quantities to optimize, right? If we had a measure, I agree that this is difficult, but if we had a measure of looking at a long-term value and quantifying that and measuring that, perhaps it will not come out as a trade-off that you're making, right? Perhaps that is the right thing. I mean, yeah, right? What do you think?
Yeah. That's also true. So basically, if you're looking at it as a long-term thing, maybe it might not come off as a trade-out. Depends on what metric you're measuring there.
Yeah.
Hello.
Hello.
Yes.
Yeah, I know a lot of people are very eager to have snacks, is what I heard.
We have a question here from the audience. Just one second.
Good evening, ma'am.
Yeah.
Ma'am, as you were talking about in the slides about the regenerative model on the fairness, so I wanted to ask, like, if any model can be prepared in which we generate some models in which, like, we can put some constraints and put some priority order on the resume as you were talking about, like the postal code and about the gender, as you were talking about that gender, aggregate gender, and you were also talking about the causation and the correlations on the graphs. Can that model be made?
Yeah, so like these are like different examples, right? But in general, yes. So I think that's what, yeah. So basically you can make, you can incorporate it when you're coming up with your loss function for the model. You can add these constraints that you choose which groups you care about, and like, a metric that you care about, like, RMSE or one of the metrics, and you can say that you want it to be within a certain threshold for different groups. So usually you can add that as constraints, and then you will have, like, you can make a fair model. So there's like a lot of work around that actually.
Like, ma'am, why the most of the companies don't do it? Like,
so it is expensive. So, okay, number one, to develop a custom model is expensive. A lot of companies actually end up using off the shelf, whatever is available, right? So in libraries. Number two, like even if you incorporate this, it takes a fair bit of, you'll have to evaluate it, and it is a fair bit of effort, right? So that's the reason big companies would actually, people who have, like, companies that have a lot of ML bandwidth would actually end up exploring these kind of solutions. But then if you are looking at a faster turnaround time for your project, then you typically use some of the off-the-shelf algorithms, and then use the pre-processing and post-processing things, which you anyway might in some cases, but like you could use some of these post-processing techniques, for instance.
yes, ma'am. So I also wanted to ask that, like the companies are looking at the cost, that's more costly. So like are they putting the future of the employees and the future of the company in preference for the cost? Like if the cost is low, so they are not doing it. So like that would affect the company in any way.
I'm guessing that it depends on the budget that they have, right? So basically, you can hire X number of people, you have X amount of time to do projects, and you want to do the best you can in that, right? That's how most people look at it. So you want to do the best you can with the resources you have, right? So if there is a custom solution that you can build that that can solve the problem and you have the resources for it, good to go for it. But if you don't have the resources for building that custom solution, then you take an off-the-shelf solution and do the best you can with it. And then if it is like giving a really bad outcome, like you measure your, maybe if you care about fairness a lot, you measure those metrics, it's not helping you. Then you think what else you can do, right? So typically,
Thank you, ma'am.
Any other questions?
We have another question here.
Good afternoon, ma'am. It's Ravinder. Usually, how much time a company will take to adopt or establish a ML-based solution in their company?
so it differs from company to company. So in bigger companies, it could be like, 6 months to even 1 year. But if you go to startups or companies like that, then it could even be like a month, right? So it really depends on the size of the company and the culture of the company, right?
Okay, ma'am. And there is another, like for a startup, how much resources are needed to provide a solution to a company, or for their own product if they want to develop ML-based solution? Or it vary based on the startup to startup, or based on in what area they are operating?
Right. So if they want to develop an ML-based solution, then they need to hire some people to develop that solution, perhaps, and then they need to have some infrastructure, typically, right? So many of this depends on the solution. So if you don't need like GPUs, and if you don't need any fancy infrastructure, and if you like, depends on the data that you have, amount of data and things like that also. If you don't need anything fancy, then you don't need a lot of infrastructure. Infrastructure might be very cheap, and you can hire somebody to do that. But then some problems are harder to solve and might take a bigger team. So also, like, as you keep growing as a company, you have more and more problems to solve. So you might like end up spending more resources also.
Thank you, madam, for this. And is there any resources or any block is there on which the startups are providing what kind of problems they faced and how they tackle these things? Means
Um,
I'm making sense, or should I repeat my question?
yeah, I'm not sure if there's a specific blog or a website I know that talks about these problems explicitly. If I can think of any, I will maybe send it to Anirban.
Yeah, okay. Thank you, madam. Thank you so much.
Seems like there are no further questions from the audience.
Well, let's thank Lavanya. Thank you. Thank you
so much, Anirban, for having me
Thank
part of the summer school.
Very informative. Thank you. All right, take care. So we'll meet in again. Let's take 3:50. Let's